Sorry, from NIST, so nearby, and he'll tell us a little bit about some studies of superlattices of bismuth ferrite.
Thank you very much. Hi, everybody. Thanks for the talk. I really appreciate it. So I'm Colin Heikus. I'm currently at the NCNR doing neutron scattering. And so this is a collaboration we've had going now for a while on kind of the coupling between magnetic ordering and polarization domain structures in bismuth ferrite and using superlattice engineering to attempt to alter this. So, come on. So I think we're all pretty familiar with bismuth ferrite at this point. A lot of the interest in bismuth ferrite as a multiferroic really stems from the idea of coupling the polarization state and the very high polarization state you get in bismuth ferrite, and coupling that to magnetic switching, and being able to control magnetism in bismuth ferrite through an exchange bias with the flipping the polarization state with a field. And so bismuth ferrite's also exceedingly interesting due to all the various domain wall effects you get. You can have these charged domain walls, conducting domain walls, a whole zoo of various possibilities given the rhombohedral or pseudo-rhombohedral structure that bismuth ferrite forms in thin film states. So also, these domain walls not only are conducting, they can also be photoconducting, and there's lots of work, using bismuth ferrite as or attempt to use bismuth ferrite as kind of a novel photovoltaic where you get kind of enhanced photocurrents due to the internal fields, or that's the idea. And then also, bismuth ferrite has a couple different interesting kind of ground state ferroelectric structure-based interests where you kind of tune through a morphotropic phase boundary, both with strain, where you can kind of tune between this tetragonal phase and this rhombohedral phase and mix states it and get this enhanced piezoelectricity. But also, you can do this with pressure and chemical pressure and all sorts of things. And then also, with chemical doping, you could tune through a second morphotropic phase boundary, where you're going from this standard R3C-like ferroelectric rhombohedral bismuth ferrite state. You dope in any rare earth, in this case it's samarium. You enter this intermediate regime where you get this 4-by ordering, which is like a lead zirconate-like structure, so antiferroelectric-like structure. And then you get high enough and you transition into a paraelectric orthorhombic structure, similar to lanthanum ferrite or other rare earth ferrites. Now, the important thing here for what I'm going to talk about is, I'm going to mention magnetism a bunch because I do neutron scattering. And in this case, through this whole phase, as far as we know, for this region, it's a G-type antiferromagnet, where in thin film case, you kill the cycloid for most strain states. And in this case, it's just also a normal G-type, but the tilting patterns are different going from the rhombohedral state to the orthorhombic state. And so the question is, so not using strain and not using chemistry, can we somehow tune these ground states, these ground polarization states, and perhaps couple to the magnetic states using interfacial or boundary condition engineering? And so what we've done is we've grown a bunch of superlattices, and what we're doing is we're actually growing bismuth ferrite and lanthanum-doped bismuth ferrite. So in this case, the bismuth ferrite should be in the rhombohedral ferroelectric state, and the lanthanum ferrite should be well into the paraelectric state. So you kind of have this frustration of a polarization building up through the bismuth ferrite, as well as a paraelectric state in the orthorhombic system. And so we've grown a bunch of these. MBE is very nice for this because we can grow the bismuth ferrite in an absorption-controlled regime where the thickness is controlled by only one flux instead of having to balance flux to get correct stoichiometry. So in this case, we can grow absorption-controlled both for bismuth ferrite and for 40 to 70% lanthanum-doped bismuth ferrite. So this is well into this regime where we're not anywhere close to this morphotropic phase boundary. Of various characterization techniques, so diffraction, reflectometry, and X-rays, various TEM. I'm going to show a bunch of TEM data. EELs, STEM, all indicate good growth, high-quality films. And as I said, this chemistry is important. All of our lanthanum-doped layers are well within this paraelectric state. And so you get a characteristic, benchtop X-ray here where even though we only have, our only contrast here is just the lanthanum on the bismuth site, right? That's the only Z contrast we have. We still get nice, sharp superlattice reflections. This is for a 10-10 superlattice, 20 repeats. We get these nice, superlattice reflections throughout the whole series, and they index correctly. So here's a nice TM image of one of these films. And so you can see, once again, high quality, but we have clear, nice, clean interfaces throughout the whole film. And so then, what happens when we actually go and we image the displacements of the various atoms to try to map out the polarization state? And so what you see is that you start to see this interesting up, up, down, down pattern. which is very similar, at first glance this is very similar to the lead zirconate-like antiferroelectric state. And so, so we get multiple different domains of this, and these domains can coexist with, this is a ferroelectric displacement pattern. And so this is a very similar state, or by TEM so far, this looks like a very similar state to what we see at the morphotropic phase boundary. But in this case, we don't have morphotropic phase boundary composition in the bismuth ferrite. We have pure bismuth ferrite interface, and we have regions where it's just ferroelectric, but for the most part, we have these nice full field for this particular film. And so this is a 14 repeat film. So you might immediately ask, okay, so you have lanthanum diffusion, and that's what's going on here. You have some sort of lanthanum diffusion through the film where you're actually at the morphotropic phase boundary somewhere, and that's triggering this. And so Lena's group did some nice EELS mapping from these films, and what we see here is that we have nice, no significant lanthanum interdiffusion. And I think the error bar on this is like less than 2% lanthanum possible in the film through these EELS images, and so that puts us, both the bismuth ferrite is well on the rhombohedral side of the morphotropic phase boundary, and the lanthanum doped bismuth ferrite is well on the orthorhombic side of the phase diagram. And yet we're seeing something consistent with this quarter spot ordering that is this lead zirconate-like phase. So we had some collaborators do some calculations to see if this is a stable antiferroelectric phase. And so yeah, they stabilize the lead zirconate phase in bismuth ferrite, but they also stabilize 3 other possible structures of this that corresponds to this up, down, down modulation of these atoms here. And so at this point, we know that we have this. All these are the antipolar phases. So we know we have something where we have this pattern in the TEM, but it could be any of these phases, and they're still working to kind of figure out what the lowest energy phase is and determine what's going on here and why we're driving this. But clearly we have these other non-R3C-like structures nearby in energy space, and just by coupling to the, making superlattices here, we've stabilized a new ground state. So not all of our, so the other thing is this PBZ-like structure can't be stabilized with strain alone. And so you can see that here where you've got the R3C phase is stable over all strain states here that they calculate. And that's kind of consistent with the fact that nobody's really seen this just making monophase BFO on various substrates. And a lot of work has been done with this for the tetragonal and the morphotropic phase boundary there. So that's not the only phase we see in these films. We actually see a huge zoo of possible ferroelectric or polar systems, and they can coexist. So clearly, this interface engineering is right on the edge of some instability with the polar ordering that you get. And so here's an example where we have these nice 180 degree, 190 degree domain walls throughout a whole film. And so here's a region where we have this orthorhombic antiferroelectric stripe phase. And then here's a system where we have this mixed phase region where we can go from, and this is actually, there's a couple different other antiferroelectric phases I don't think I'm going to get to for time, but we also see other other modulations of these sites that give us other antipolar phases. And they can all coexist in a single film. And we're still trying to figure out what the control parameter is to isolate one versus the other. But that's an ongoing work. And also, so that you can ask the question, okay, so we have these polar distortions, and unfortunately, we can't grow these films with electrodes where we can switch them easily. Or we haven't been able to yet. So next best thing, we have some PFM showing kind of the topography here, and then you got the amplitude and phase images here showing that we do have regions of piezo response, showing that this is a plane view, right, of coexistence of regions through the film with both ferroelectric ordering and non-ferroelectric ordering. And so this corresponds, right, like looking down through the film to regions of antipolar and potentially ferroelectric regions. So I said I was going to talk about magnetism. And that's a real question here. So we have some novel polar ordering, and we know bismuth ferrite has a strong coupling between the ferroelectric state and the polar ordering and magnetism. And you can, that's the whole electronic control of magnetism thing. So as a neutron scatterer, we uniquely are capable of coupling to the magnetic moments in a film. And in particular, we're going to use a technique called polarized neutron reflectometry here. And I think for this audience, it's good for me to explain what's actually going on here so you can get a sense of what we're doing. So in this case, we have neutrons that are sourced from our reactor. and they come down in a reflection geometry, and they reflect off the surface and go to our detector. And we get some profile similar to X-ray reflectometry, where this structure is due to Bragg scattering, as well as of the thickness of the film and the contrast of the scattering density of the substrate with the film. And you get a sense of roughness, and you get a sense of film thickness out of the Q spacing of these wiggles, as well as how damp they are, how underdamped they are. So we can also do this with a polarized neutron beam, now where the neutrons couple differently to opposite directions of magnetization over the length, the correlation length of our neutron. And so in this case now, for a magnetic sample that has a moment here, we get two different scattering profiles for the opposite, up, polarized. So neutrons that are polarized up that come out up, and neutrons that are polarized down that come out down. And we can also do the cross terms too, and that gives us kind of an orthogonal component of the magnetization. So we get some data set, and typically we think about this in terms of not intensity, but rather a differential intensity normalized by the sum of the intensities, so like a spin asymmetry term. So we take this data, we then model it with what we know of the structure from various X-ray or TEM techniques, and from doing the growth ourselves, we know what we think we have. And we can compare this to reflectometry consistently and feed this back into a model until we get something that converges and generates a nuclear profile. So this is the nuclear contrast, and a magnetic profile and the magnetic contrast, and this is an incoherent thing here. And we also can back out the direction of the magnetization with respect to the field we're applying. So in this case, we're actually applying a magnetic field to orient the moment, so we don't have to deal with domain effects. So what you get is you get depth resolved magnetic and nuclear profile, and you get angstrom resolution here. So this is one of our films. So this is a 3-repeat film now. And I should note that the TEM of this film shows actually that we get an anti-ferroelectric pattern throughout the entire film, which maybe is unsurprising because there should be some crossover regime where they're coupled. And this is actually a composition that is in the morphotropic phase boundary, despite still seeing clear segregation where the bismuth ferrite is bismuth ferrite and lanthanum bismuth ferrite is bismuth. But if you average over the whole system, you're in the morphotropic phase boundary, which is kind of what's always going to happen for these 40% lanthanum films with 50-50 superlattice ordering. So in this case, this looks really impressive because this splitting should all come from magnetization, but I should warn you that terbium scandate has a really large anisotropic paramagnetism, and we couple to that too. So a large portion of this spin asymmetry is coming from the magnetization in our substrate, but because we have depth profiling, the Q dependence and where we deviate from Q gives us some the ability to tell apart the magnetization in the substrate from the magnetization in the film as we fit our model iteratively. And so this fit, so you can see my fit here to this data. This fit corresponds to a profile where, in this case, I know I have a superlattice, but I've only measured out in Q far enough where I wouldn't actually see the superlattice ordering for such a tight. So I'm actually simulating this with a model, with an alloy model where I'm assuming just a incoherent mixture of lanthanum and bismuth ferrite at the correct composition. And so, given this model, I have some substrate nuclear profile, an alloy, and then some roughness of the surface. And the same thing I have. This is a nuclear roughness, as opposed, that the nuclear roughness can be different from the roughness you measure with X-ray, just because of the coherence length of the neutrons and how sensitive we are. So then I have my magnetic profile, and so I see a really high magnetization in my substrate. But then my fits always converge to something that looks like a uniform magnetization. And in this case, I'm not allowing the magnetization to oscillate with the periodicity of the superlattice, just out of interest of getting a nicely fitting model. But if you look, the parts where I'm missing the asymmetry are in this Q range around 0.05. And this Q range is interesting because it corresponds to like 1/4 of the superlattice repeat. So something's going on here where we have what looks like a uniform, or some non-trivial magnetization in our film that's about an order of magnitude higher than what's expected for bismuth ferrite. And so our fit corresponds to when we convert their scattering density to like almost a half MUB per iron site. And that's assuming a uniform magnetization. So if it's only in the bismuth ferrite, if it's only in the lanthanum, if it's only at the interfaces, it's actually a higher magnetization. Now I should note that this is under a 3 Tesla field. So this does not survive to relaxing the field. So this is not a ferromagnetism that we're seeing here. This is some sort of anisotropic paramagnetism or free spins in the film. And we expect this might have some sort of interfacial effect. because we don't see this for films that have fewer interfaces, basically, that have a lower interface density. And so we've also done elastic scattering, just to note that our elastic scattering is consistent with half-half-half G-type ordering with no cycloid. And with that, I'm going to leave at my conclusions. So we've grown these superlattices, and we have this novel polarization state. We're still trying to figure out what the control mechanism is for this, but it certainly seems that when you start to make superlattices of bismuth ferrite with effectively no strain here, because we're growing on a system where we have less than 0.5% strain from the substrate, and then we have the lanthanum and bismuth are roughly the same size, so we're not really getting any sort of superlattice buildup of strain in the system. We have an apparent paramagnetization at 3 Tesla in these systems at 5K. And we see a clear half reflection with no evidence of cycloid. Now, I should note that we've also tried field dependence of the elastic scattering. And so what we see is a slight field dependence of the scattering intensity at this half peak, but we're still trying to run this down and make sure that this is real. And with that, I'll thank you and take questions.
Okay, we have time for some questions.
Actually, you could resolve the problem with the magnetism if you would use...
I'm sorry, I can't hear you.
You could resolve the problem with the magnetism if you would use μSR, because this is depth dependent and you can really trigger that. Yeah,
so we're looking into that for this system as well. Nominally, the reflectometry should have a very similar. The μSR will tell us whether it's the film, but you don't really have the resolution with the soft μSR to tell the difference between. You can do kind of 15 to 20 nanometer steps.
So you can even do it on the surface.
You can do just on, yes, you can do just on the surface, but as you start going in the depth of the MSR, you start to lose spatial resolution as you get. So you can tell at the top versus the bottom, but for a film this thick, you start to, we're talking about a 70 nanometer thick film, and so as you start to get an energy broadening, right, of the MSR.
That's new to me, actually. I know that it's very precise, and you can detect any magnetism at any depth in the
Yeah, it's very sensitive to low magnetism, but it's the depth profiling with soft MSR is very dependent upon just the energy. You pick where in the film you deposit the muons, and so that the thickness band of where the muons are and for your resolution spatially is limited by the energy you have to use to deposit them. So as you progress through the film into the substrate, you broaden out your muon profile significantly.
Nevertheless, I think it's the most precise method.
Yeah, no, absolutely. We're definitely thinking about that.
Any other questions? All right, let's thank our speaker one more time. Okay, so our next speaker is Dhiren Pradhan here from the Carnegie Institution for Science, and he'll tell us a little bit about some interesting composite multiferroic materials.
Good morning, everybody. Thank you. So today I am going to talk about room temperature multiferrogem in PFN nickel zinc iron composite thin films, and I am working with Professor Ron Cohen, and this work is collaborated with Oak Ridge National Laboratory and Professor Ram Katiyar, Salini Kumari from West Virginia University, and Professor James Scott. So my outlines are why composite structure are really needed, and the mechanism of magnetoelectric coupling in multiferric composites, then my motivation, then my sample preparation, then results and discussion, then I will conclude my talk. So in 1894, Pierre Curie predicted that materials should exist which can be polarized by a magnetic field and magnetized by an electric field. Perhaps this leads to the discovery of multiferrous material. Multiferric materials are those materials which have at least two primary ferroic order exist in same phase. The primary ferroics are ferroelectric, ferromagnetic, ferroelastic, and ferrotoroidic. So, due to the mutual frequent incompatibility between electric and magnetic order, there are very few multiferroic exists in nature, and among them these are some common examples of multiferroic materials like bismuth iron oxide, bismuth manganese oxide, lead iron niobium oxide, yttrium manganate, and magnetite. Among all, only bismuth ferrite is known as the room temperature multiferric materials, but it cannot means still it is not applicable for practical device due to its high leakage current and high dielectric loss. And the other multiferric material has either the ferroelectric or ferromagnetic transition below room temperature. So due to this large independency between the ferroelectric transition temperature and ferromagnetic transition temperature, the magnetoelectric coupling is very small. So in order to achieve strong magnetoelectric coupling above room temperature, means composite structures are needed. So why multiferric composite structures? Means the advantages are we can get combined high values of electric and magnetic polarization at room temperature, and we'll get higher effective magnetoelectric coupling coefficients, and we'll get wide range of operational temperature for multifunctional application. Means we can get both means the ferroelectric and ferromagnetic transition above room temperatures. So during the synthesis of composites, as it is means ferromagnetic and ferroelectric phase, we have to taken care a lot of things like chemical. There should not be any chemical reaction between the ferroelectric and ferromagnetic phases, and the electrical resistivity of ferromagnetic phases should be very high to minimize the leakage currents, dielectric loss, in order to withstand the high electric field. And during the synthesis, mechanical defects such as pores of the ferromagnetic and ferroelectric phase should be taken care, and we should grow like atomically perfect epitaxial growth of either multi-layer or composite single layer thin films for perfect mechanical strain transmission. So there are like three types of composite structure. One is 0,3 particulate nanocomposite means in a ferroelectric matrix there should be ferromagnetic particle, and another is means multi-layer of alternative ferroelectric and ferromagnetic material, and another is 1,3 vertical heterostructure with one phase nanopillar and embedded with a matrix of other phase. Magnetoelectric coupling is normally indirect coupling, and it is via strain. Here there are two types of coupling. One is direct magnetoelectric coupling and another is converse magnetoelectric coupling. The direct means by applying a magnetic field we can change the electrical order parameters. Here when we apply magnetic field, due to magnetostrictive deformation occurs in magnetic phase and it transfers to the ferroelectric phase. Then due to the piezoelectric effect, we can see the changes in order parameter. And in converse magnetoelectric effect, by the application of electric field, we can see the changes in magnetic order parameters. So we have synthesized PFN and nickel zinc iron oxide composite thin films in order to achieve room temperature multiferroism with strong magnetoelectric coupling. Here PFN means PFN is one of the multiferric material, and it has monoclinic structure. It has high piezoelectric coefficient, low loss tangent, and its ferrority TC is around 379 to 385 Kelvin, and it has excellent ferroelectric, magnetic, and ferroelastic properties. And nickel zinc, we have chosen the magnetic material as nickel zinc iron oxide, as it is a ferrimagnetic material, and it has cubic spinel structure at room temperature, and Tn nil temperature is 600 K, so that we can get the composite structure have a magnetic transition above room temperature, and it has low coercivity, high resistivity to withstand high electric field and high magnetization coefficient. It has good thermal, chemical, and structural stability, and this composition, nickel 65 and zinc 35 composition possesses the highest saturation magnetization in the entire nickel zinc series. So this is this is our means 1 minus x PFN, and means we have synthesized 10%, 20%, 30%, which can be abbreviated as PFN, PN1, PN2, and PN3 throughout the talk. So we have synthesized the thin film, single layer thin films, because previously we have synthesized some multi-layer, but due to substrate clumping, we could not get such high magnetotic couplings. So that's why we plan to grow some single layer thin films with a PFN and NZFO composite. And we have started this synthesis with a single target of PFN and nickel zinc iron oxide, and these are the optimized parameter. We have grown at 20 milliliter of oxygen pressure. The substrate temperature was 600 degrees Celsius, and we have annealed the sample around 700 degrees Celsius for 30 minutes at 300 torr of oxygen in order to avoid oxygen vacancy. And the laser frequency was 5 Hz, and the laser frequency was 5 Hz, and the fluence was 1.5 joule per centimeter square. And the bottom electrode is lanthanum nickelate, and for the electrical characterization, we have made the top electrode as platinum. So these are the X-ray diffraction pattern of pure PFN. This is a pure NGFO, and these are the composite structure. Here, in PFN and NZFO, we only observe the L00 peaks, means for PFN we only observe 100, 200, 300 peaks, and in NGFO we only observe 400 peaks. So, and in composite case, we also only observe the L00 peaks. Here, in the composites, we observe both the both phases of PFN. The H peaks corresponds to PFN, and the end peak corresponds to the NGFO. So we observe both PFN and NZFO peaks, and so means we can tell that the formation of composite structure. And here we also observe with the increase of magnetic content, the peaks of the intensity of peak of NGFO goes on increasing, and we did not find any intermediate or secondary phases and peaks from lead deficient paracolor phases. So from the X-ray diffraction, we can tell that the quality of the films are good. So in order to confirm in our thin films whether all elements are present or not, we have carried out the XPS studies. So here all lead, iron, niobium, and oxygen, and nickel, zinc peaks are present. So observation of all photoelectron characteristics of lead, iron, niobium, nickel, zinc, and oxygen confirms the presence of all individual elements. And for the representative of all the films, we have carried out. I have presented only this. So this is the dielectric property in order to prove the ferroelectric phase transition of all the composite structures. So this is the dielectric spectra of PFN, PN1, PN2, and PN3. Here means as the magnetic content goes on increasing, the ferroelectric phase transition also, ferroelectric phase transition temperature Tc goes on increasing, and all this composition shows like relaxer behavior. Here with increase of magnetic content, you can see for PFN it is around 400, and PN1 it is around 430, and for PN2 it is 440, and for PN3 the ferroelectric phase transition is around 460 Kelvin. So in order to confirm the ferroelectric nature of all the thin films, we have studied some band excitation PFM measurement. So here we have polled the sample with positive and above positive and negative 5 volt. So we can see the phase contrast in positive and negative area. So from this we can tell that all the composite thin films exhibit ferroelectric character. But this behavior can also be seen in some non-ferroelectric material, so due to electrostatic effect. So in order to avoid, means in order to rule out that our material means this behavior is not due to electrostatic effect, we have carried out some other studies. So here, this is the this all these are data of PFN, pure PFN1. So here we observed, like we have observed PFN. This is amplitude versus voltage. We have means we got butterfly amplitude behavior in PFN thin films, and with a phase flipping of 180 degrees Celsius. 180. And we have carried out also the piezo response. Here is the means out of field measurements, means of field measurement, and this is the in field measurement. And we have done also in field minus out of field measurement. If it is linear, then there is no periodicity. So it is highly nonlinear. It can be concluded that it is periodic. And we have subtract the linearity part also, and here we got the nonlinearity means. Now we can safely say that our means all the films are ferroelectric in nature. So we have carried out some temperature dependent piezo response measurement in order to corroborate the bulk ferroelectric phase transition, and this is the tip induced ferroelectric phase transition. So as the temperature increases, the piezo response goes on decreases, and above 125 degrees Celsius, there is means the piezo response vanishes. Hence, in both the case, means out of field and in field, and this is the room temperature in field minus out of field. It is nonlinear, and in field minus out of field measurement, it is highly linear, means there is no periodicity above the phase transition temperature. So here are the ferroelectric means bulk. This means the cross is the surface phase transition, and this is the bulk ferroelectric phase transition. Here means except PN2 means all the bulk and ferroelectric bulk and surface phase transition are approximately same. Then we have studied some magnetic properties of composite thin film. Before studying of composite thin film, we have studied the magnetic properties of nickel zinc iron oxide thin films. Here, this is the low temperature MH loop from 20 Kelvin to 395 Kelvin, and this is the empty curve of low temperature. Here, means we observe a large bifurcation, which indicates that it is like slightly disordered type ferromagnetic system. And here, and as the temperature increases, the magnetization goes on decreases. And here, in high temperature magnetization versus temperature curve, we found the magnetic transition, and the magnetic transition is the ferromagnetic to paramagnetic transition is probed around 700 Kelvin. That's why we have included that this nickel zinc iron oxide as a magnetic candidate in our composite structure. So these are some these are the magnetic properties of composite thin films. Here you can see the PN1, PN2, and PN3 thin films. It has also some very less coercivity, and it has less remanent magnetization. And here also we observed that as we increase the magnetic content, and these are the field-cooled curve of taken at 1000 Oersted. As we increase the magnetic content, the magnetic transition goes on increasing. And in all the means the PN1 and PN2 case, the magnetic phase transition is observed around the ferroelectric phase transition temperature, plus minus 10 or 20 degrees Celsius. So, and in this is the PN3 one, but we are getting around 550 Kelvin. Here, all the composites of typical ferromagnetic like hysteresis behavior above room temperature with high saturation magnetization, low coercive field, and low remanent magnetization. And we are also performing some fast principle calculation in order to understand the effect of magnetic content on origin and nature of phase transition, and the ferroelectric magnetic and ferroelectric and magnetic properties, and the nature of magnetic coupling, whether it is PM square, P square, M square, P square, M of all the composite thin films. So, means we have, in conclusion, we have synthesized high quality of PFN and ZFO thin films, and the presence of both PFN and ZFO phases with 0-0 pseudocopic reflection confirms the formation of the composite with highly oriented in nature. The ferroelectric nature of the thin films are confirmed by band excitation PFM. The ferroelectric magnetic transition TC are observed above room temperature, and both the TC increase with increase of magnetic content. All the composites show ferromagnetic-like hysteretic behavior above room temperature with high saturation magnetization, and high amine coupling is expected for all the composite as the ferroelectric and ferromagnetic TC are very close to each other. And we are acknowledging Carnegie Science, Oakland National Laboratory, Office of Naval Research, and ERC grant, and computational support from HPCM. Thank you very much.
All right, any questions?
I understand that you didn't do any electric or magnetic field dependencies of your
Yes, this is our next step. This is our next step to study some magnetoelectric coupling.
Because at present you cannot say anything about a cross-coupling.
No. It is reported that if your ferroelectric transition temperature and magnetic transition temperature are close, then it means magnetodielectric coupling is there. But it is the indirect evidence. We are planning to study magnetodielectric coupling very soon.
It should be proven, of course.
Yes.
Other questions? I'll ask one real quick. In the PFM data, what was the different contrast for? There was like some splotchy yellow things. These are is there phase separation? Like what am I looking at?
These are some, I have mapped the phase between what is the phase. I did not delete those things. So I mapped those areas so that to know whether the phase are really opposite to each other or not.
Other questions? All right, let's thank our speaker one more time. All right, so our next speaker is Binju from the University of Arkansas, and we'll continue talking a little bit more about the magnetic structure of bismuth ferrite.
Thanks, Chairman. Hello, everyone. Also, I want to thank the organizers for giving me this talk. Today, I want to speak about spin cycles in multiferroic bismuth ferrites in films. Before I start, I want to first acknowledge my collaborators. For theory, I work with Rohan Blesch at the University of Arkansas, and we collaborate with Bertrand Dupé from Germany. And for experiment, and the neutron diffraction measurements on 110 thin film was done by people in Australia, in particular University of New South Wales, the groups of Valenor and Woolwich. And I also want to thank the financial and computational support. So BFO is a very rare room temperature multiferroic. The ground state has this rhombohedral symmetry and with the space group R3C. It has a very large polarization pointing along the 111 direction. It has a very high Curie temperature above 1,000 Kelvin. It also has antiphase oxygen octahedral tilting along the polarization direction. And its magnetic structure is approximately G-type antiferromagnetic. the new temperature is more than 600 Kelvin. For bulk BFO, it also has this type 1 cycloid with a wavelength of modulation of 62 nanometers propagating along the 1-10 direction. In some previous works, there is a proposed converse spin current model to explain the existence of this spin cycloid. Because of this cross product between Mi and Mj, so this term favors a non-collinear spin order. This C is coupling strength, and Ui is the electric dipole moment on the position I, and Eij is a unit vector connecting position I and j. So in this talk, the question I'm trying to discuss with you is that can we use this spin current model to understand different magnetic structures in BFO? First, let's see what are the magnetic structures that have been observed in BFO. We already know the bulk BFO has a type 1 cycloid, but this cycloid can be destroyed in many ways. For instance, by applying a strong magnetic field, strong electric field, high pressure, doping, or large epitaxial strain, either compressive or tensile. Under these conditions, there is a transition from the cycloid state to a canted antiferromagnetic state with a weak ferromagnetization. For simplicity in the talk, I'll just call it AFM. There is also a type 2 cycloid in BFO. For instance, in 001-oriented film, under small compressive strain, the type 1 cycloid is stable. But for small tensile strain, the type 2 cycloid with a propagation direction of 1-2 is more stable. The same type of cycloid is also observed in 110-oriented film by our collaborators. And strontium titanate is the substrate. How can we understand these different magnetic configurations? We know that the occurred magnetic structure is the one that minimizes the total energy. And here is the magnetic energies we considered in our effective Hamiltonian. The first term is a long-range dipole-dipole, magnetic dipole-dipole interactions, which is relatively small. And the second term is the short-range exchange interactions, which is strong, and it favors the antiferromagnetic order. And the three terms in the middle are the interactions between the magnetic moments with other degrees of freedom, including the dipoles, the antiferrodistortive tiltings, and the strains. And the next term is the DM interaction, which can cause the spin canting. The last term is the converse spin current model, which is also a DM type interaction. For this last term, the spin current term, we consider both first and second nearest neighbors. We call them C1 terms and C2 terms. In total, there are 6 first nearest neighbors and 12 second nearest neighbors. And the first nearest neighbors have those neighbors in those 1, 0, 0 directions. And for the second nearest neighbors, they are in those 1, 1, 0 directions. In previous works, it has been demonstrated that by only considering the first nearest neighbors or by only considering the second nearest neighbors, we can reproduce the type 1 cycloid propagating along the 1-1, 0 direction. But in this talk, I'll show you that to explain all the magnetic structures in BFO, we may have to consider both the C1 terms and the C2 terms. So what we did is performing Monte Carlo simulations based on the effective Hamiltonian. In the Hamiltonian, we consider not only the magnetic energies I just discussed, also we consider the energy related to the dipoles, the tiltings, and the strain. And we use a supercell size that is 12 by 12 by 12, and 80,000 MC sweeps for convergence. And we study bulk BFO at the temperature of 10 Kelvin. What we did is we varied the C1 and C2, these two parameters, independently. C1 is for first nearest neighbor, and C2 is for second. And for each pair of C1 and C2, we find the most stable magnetic structure. And this magnetic structure is determined by performing the Fourier transform. And this is our calculated phase diagram. The x-axis is for C1, and the y-axis is for C2. Each different color represents a magnetic structure, and a different color for different magnetic structures. As you can see, if we keep C2 being 0 and we increase C1, we'll encounter these different phases, starting with AFM, then there's one here, 1, 0, 0 cyclode, then 1, minus 1, 0 cyclode, then 1, 1, 1 minus 1 minus 1 cyclode, then 1 minus 2, 1 cyclode. On the other hand, if we keep C1 being 0 and increase C2, we will have the AFM, then 1, 0, 0 cyclode, 1 minus 1, 0, then there's another one, 2 minus 1, 0, and then 1 minus 2, 1. We also see that for each magnetic configuration, it forms some shapes of bands. And these bands are extending in the direction that with increase in C1 and C2. So not that way, but this way. So just to mention that in total, we have found 6 different types of magnetic structures, including the AFM and type 1 and type 2 cycloids that was observed in experiments before. We also predict 3 new types of cycloids, which were not known before. And the difference between these 3 new types of cycloids compared with the known one is that if we sum up the 3 indices of these 3 numbers, it is an odd number instead of an even number, which means along the propagation direction, these 3 cycloids will be the antiferromagnetic cycloids instead of the ferromagnetic one. Now let's see how we can use the C1 and C2 terms with those 1, 0, 0 neighbors or 1, 1, 1, 0 neighbors that can produce propagation directions in different directions. And so this is the spin current model. And because for the cycloid structure, Mi cross Mj will be either in the same direction or in the opposite direction. So we can rewrite this term as a weight times a unit vector. And then we do this cross dot product, we change it to dot cross product. And then to minimize this energy, the Q vector, which is the propagation vector, is simply the weighted sum of these Eij vectors. And the Eij are for the first neighbors or second neighbors, which are in those 1, 0, 0 or 1, 1, 0 directions. Now let's look at some examples. First, we keep C2 equal to 0 and we increase C1. We first have this AFM phase because in the antiferromagnetic case, Mi cross Mj will be 0. So there's no contribution from any neighbors to this magnetic structure from this term. Then for 1, 0, 0 cycloids, we have 2 contributions of the same weight because these are the neighbors that is along this 1, 0, 0 direction. And for 1, minus 1, 0 cycloids, we have 4 contributions of the same weight because this combination of the same weight, it could be plus or minus, that can give us this weighted sum in this Q direction. And then for 1, minus 1, minus 1 cycloid, we have 6 contributions of the same weight, and they can give us this Q vector. And the last one is 1, minus 2, 1 cycloid. We still have 6 contributions, but along the y direction, the weight is doubled. So we have the weighted sum in this Q direction. And that's how it works for the first neighbor terms. And for the second neighbor, C2 terms, if we keep C1 equal to 0 and only change C2, we start with the AFM, no contributions. Then 1, 0, 0 cycloid, 8 contributions of the same weight. So the weighted sum give us this direction. And then 1, minus 1, 0 two more terms, slightly more complicated, but the weighted sum is exactly that. And then 2 minus 1, 0, then 1 minus 2, 1. And then in this, taking this 1 minus 2, 1 as an example, you can see there are different ways from different terms. The opposite ones have the same contribution, so the sum is given this direction. And if both C1 and C2 are finite, the contribution will simply be a summation of the C1 terms and C2 terms. To understand why each magnetic configuration forms this kind of bands extending with increasing C1 and C2, the reason is that the C1 terms and C2 terms, they are competing. If one energy is positive, the other one will be negative. The reason is because of this Mi cross Mj term, because one is the first nearest neighbor and the other one is second nearest neighbors. And the BFO is the G-type AFM, so that gives opposite sign of this cross product. Then, to estimate the possible values of C1 and C2, we need to consider some experimental facts. Bulk BFO has the type 1 cycloid. Under small tensor strain, there's a type 2 cycloid. Also, under large field of strain, it becomes AFM. Because the energy change, the relative energy change due to the field of strain is relatively small for these different configurations. So it tells us that these three different configurations have to be close to each other on the phase diagram. And the circled region is the only possibility here, which suggests that both C1 and C2 needs to be finite. Also, over here, C1 has a magnitude that is about 1 order of magnitude larger than C2. Another interesting point is that in this region, the highlighted region, we also see a new kind of cycloid which propagates along the 1 minus 1 minus 1 direction. And it will be interesting that this can be checked experimentally later. At the end, I want to show you the scaling behavior of cycloid on 110 film. And these are experimental results with neutron diffraction. So what is found is that the cycloid period increased significantly with thinner film thickness or with the increase in temperature, in particular approaching the new temperature. So this is the thinner thickness and increase in temperature. And the spin current model may offer explanation for this finding, because if the polarization decreases with smaller thickness or increase in temperature, then this term becomes weaker. And the weaker of this term means the cycloid period is longer. Because, as you know, the antiferromagnetic order can be understood as a cycloid of infinite length. So to conclude, we have predicted the C1, C2 phase diagram for bismuth spherite. And by comparing with the experiment, it suggests that we need to consider both first and second nearest neighbor interactions for the spin current model. And C1 is much larger than C2. And we have reproduced the type 1, type 2 cycloids. And we also predict the new cycloids, in particular the 1 minus 1 minus 1, which may actually exist. Also, the period of the cycloid in 110 film becomes longer with thinner thickness or higher temperature. Thank you for your attention.
All right, our talk is open for discussion.
It's very interesting. Is there a way to intuitively kind of get a sense of how you would expect different thin film strain fields to couple differently to the nearest neighbor versus second nearest neighbor terms? So for example, you have a 001 versus 110 oriented film, and therefore you have in-plane pinning and out-of-plane relaxed. And is there kind of an intuitive way to think of how the ratio between C1 and C2 would change with these changing biaxial strain fields?
In my understanding, there will be some change, but the general form of this phase diagram may remain similarly. It's just the shift of the boundaries, because around the boundary, it means the two magnetic configurations have very close in energy. So by changing the strain, it is this boundary may shift towards one phase or the other phase. So,
but I think I'm asking, how does strain move you through this phase space?
Yeah, this is some ongoing work, and I think, for instance, I remember if I increase the tensile strain, it may favor slightly more this 1-1 cyclode. So the area for this type 1 cyclode will be smaller, but for compressive strains, the other way around, that the type 1 cyclode may expand a little bit.
But that's assuming hydrostatic-like strain fields, right?
Yeah.
Okay. Thank you.
Actually, can I follow up on that? I'm also curious. So as you change the strain, you can also potentially change the contributions from the other energetic terms, like the short-range exchange and the Dalachinsky-Maria. I mean, this seems like it could get very complex as we start to do strain, because that's what we can do experimentally. So I'm curious what your thoughts are on the other contributions as you make these changes.
Yeah, that's a very good question. Actually, when I just answered the first question, because this is a very heavy calculation, it's about 40,000 because we need to run the molecular dynamics simulation for each pair of C1 and C2. So for the preliminary result, we just change the C1 and C2 and calculate the energy. But in principle, we should relax the structure again and see what's going on, and that would be more accurate.
Yeah, we've seen some things recently where we think under larger strains, the exchange interaction becomes quite important relative to the Dalachinsky-Maria interaction. So yeah, maybe we can talk about it offline, but yeah, it's a really good question.
Okay.
Yeah, go ahead.
I'm sorry, maybe I didn't hear well. Did I understand that C1 and C2 were fitted to some large-scale calculation of the whole effective Hamiltonian? And are there some more direct way how to get from ab initio the estimation of C1 or C2?
These two, we treat them as parameters. So that's why we change C1 and C2 and see which area may give us this good explanation for the experimental result. So they are not fitted by DFT or anything. It's just parameters.
Any other questions for our speaker? Okay, great. Let's thank our speaker one more time. All right, so our next speaker is Chengsong Zhu, who is also coming from the University of Arkansas, and we'll look at some interesting other phases in bismuth ferrite.
Okay, thank you. Hello, everyone. First, I would like to, I'm Chengsong Zhu from University of Arkansas as a postdoc of Laurent Blaise. First, let me thank the organizer to give me this opportunity to present my work, and also thanks to the university and the supporters. Today I'm going to talk about the first principle prediction of multiferric hexagonal P63CM and hexagonal-like P1 phases in the epitaxial 111 BFO films. First, I will go through the rareness of multiferrics and quickly look at the two typical ones, bismuth ferrite and yttrium manganese, and then we will look at the epitaxial strain engineering. After the methods, we will look at the predicted phases in the order of increasing tensile epitaxial strain, and we will also have a conclusion. First, we know that the bismuth ferrite is well known for as the first room temperature multiferrics. It has a very strong polarization due to the large displacement of A-site bismuth and also its lone pair. And also the antiferromagnetism G-tap originates from the B-site iron. There is a relatively weak coupling between the two quantities because they are from different sublattices. Another example of a multiferric is the yttrium manganite. It is known for improper ferroelectricity, where the polarization is induced by the primary order parameter K3 mode, the tilting mode, and also the non-collinear antiferromagnetism from the geometrically frustrated antiferromagnetism. The coupling between the polarization and the magnetism is a little bit stronger. The two quantities are mediated by the K3 model. So we want to, we are talking about this because we want to deliver the message that the multiferrics are quite rare, and one useful method is the epitaxial strain engineering to create new multiferric phases. For example, when using the strong comparative epitaxial strain, the T phase can be generated, and the spin orbit magneto-electric coupling can be very strong here. And also for rare earth manganites, rare earth ferrites in the hexagonal phase, the large tensile epitaxial strain can also generate the yttrium manganite type hexagonal structure. So the question is, what about the BFO if it is pulsed on the 111 substrate? Will it have the hexagonal phase, or will the lone pair of bismuth ferrite play a role in increasing the polarization? So we are using those methods. First, the DFT calculations. I will just pass this, and the genetic algorithm combined with soft mode analysis to predict new phase, and also for the magnetic structure, we use the DFT to generate exchange parameters and then put into Monte Carlo and see the ground state. First, let's look at the perovskite phases. At zero strain, since it's the 111 substrate, it's the R3. No wonder it's R3. R3C, yeah. And then when it goes toward the tensile side, it first becomes to CC phase and then CC2. Those phases looks like this. As we can see, the epitaxial strain is quite large. Then next, at even larger in-plane lattice constant, we notice that the hexagonal P63 CM phase becomes the ground state. And you may be surprised that this epitaxial strain is like more than 10%. But you may also notice that the local minimum is out of the curve of perovskite. So we think if this matter stable phase is really synthesized experimentally, there should be no strain effect here. And we also look at the paraelectric P-3C1 phase. It is always 15 millieV per formula unit higher than the polar P63CM phase. We now look at the polarization of this polar phase. As we can see, when the in-plane lattice constant increases, the polarization increases. We should note that for this phase, the polarization is pure along the C direction. It increased from this in-plane lattice constant for like 6 millicoulomb per square centimeter to this side. It's a 9 or almost 10. It's increased almost 60%. This is pretty novel because, according to our knowledge, normally when you increase the in-plane lattice constant, the polarization, the outer plane polarization should decrease, but here it is increased. And also for the yttrium manganite type hexagonal structures, it is also like this. The polar mode decreases when the in-plane lattice constant increases. So similarly to this kind of analysis, we also look at the modes, the phonon modes. When increasing the in-plane lattice constant, the primary K3 mode decreases, while the polar mode, the gamma-2 minus polar mode, increases. It's different from here. So yeah, this might be the direct reason for the increasing of the polarization. So what's behind that? Let's look at the energy landscape of the K3 and gamma-2 minus mode. At small in-plane lattice constant, the K3 has a double well. Means that this is the primary phonon mode, which is also the driving force of this phase transition. While the polar mode is a single well. That means the polar mode is induced by the K3 mode. Well, when the epitaxial strain becomes larger, we can notice that first the double well of the K3 mode becomes shallow, and then the gamma mode, the bottom of the single well first becomes flight, and then the double well emerges. So that means when the tensile epitaxial strain becomes larger, the proper component gradually come into play. Yeah, that's quite different and never reported in the yttrium manganite type hexagonal phases. And also for the magnetism, we consider the 4 typical non-collinear magnetic configurations, and the ground state at smaller in-plane lattice constant has the gamma-2 configuration and allows for the canted weak ferromagnetism. Then at even larger in-plane lattice constant, we notice there is another phase here. Again, I should stress that the local minimum is out of those curves. So if, again, this phase can be stabilized, there should be no strain here. The phase looks like this. It's pretty much looks the same with the hexagonal phase, and it is dynamically stable. Then we compare the structure between the P63CM and the P1 phase. We already noticed that the layered structure has been maintained. That means for the bismuth layer, the 1 up, 2 down, or 1 down, 2 up, it is maintained, and it contributes to the polarization, outer plane polarization. The major differences comes from the in-plane displacement. We can notice that in this hexagonal phase, the iron stay at the 1/3, the 1/3 positions ideally. While in this phase, we can notice that the iron and the oxygen, they break bond and they move against each other, and then rebound at another direction. Here we mark those bonds as as a specific iron-oxygen bond, since it will be related to the magnetism and the polarization closely. Yeah, and also we look at the lattice constant. For the outplane lattice constant C, those two red dots are for hexagonal structure, and the green ones are for the hexagonal, the P1 phase. They are quite continuously. And since it is the thin film, we confine the gamma angle to be 120 degree. And for alpha and beta angles, they are quite close to 90 degree. So we call it the hexagon-like P1 phase to distinguish with the perovskite P1 phase. This phase has quite novel polarization. Yeah, we know it has outplane up and down polarization, but here we also notice that since one of the iron-oxygen bond will break, it has three choices. Each bond breaking can lead to a different in-plane polarization state. So totally there are six-fold degeneracy of polarization in this P1 phase. And also for the polarization, besides the outplane one, there is even larger in-plane one emerges, and resulting a quite large total polarization, which is almost twice of the 8 in the hexagonal phase. For the magnetism, we calculated the iron-iron exchange coupling, which is all the iron-oxygen-iron coupling. It is found that they are all antiferromagnetically coupled. And the more this angle is close to 180 degrees, the stronger is G. The most interesting is that the specific structure and the antiferromagnetic coupling results in a spiral magnetic ground state. This is a period of 9 unit cells. And if we look at the same site in each unit cell, we can find this is a spiral structure. And we need to pay attention that this spiral structure is totally different from the DM interaction induced spiral structure. It is purely the frustration effect. Because I found that since it has a period of 9, each neighboring spin vector has an angle of 60 degrees. And we also find that the propagation direction of this of the spiral structure has a very close relation with the specific iron-oxygen bond. They always form a 6-degree angle with each other. Then we change the epitaxial strain and see how the exchange coupling changes. And then put them into the Monte Carlo simulations. We find that when we change the epitaxial strain, the exchange coupling changes, and then also the period of the spiral structure also changes. Okay. To conclude, we focus on the 111 BFO films, and then besides the perovskites, we found 2 hexagonal or hexagonal-like phases. They have quite novel magnetic and electrical properties. Okay. Thank you.
All right, any questions for our speaker? I'll get us started. As an experimentalist, I pretty much know the substrates we normally use, but to get out to those strain states, did you guys actually look and see if there are good materials?
I know your point, and that's why I'm always stressing on there should be no strain effect at this local minimum and this local minimum.
Yeah.
At another side, to stand on your point, yeah, those phases, the hexagonal one and hexagonal-like one, are highly matter stable. It's very hard to experimentally stabilize them, so we are trying to use different methods to lower the energy of these two phases. I mean, to lower those two curves toward this direction.
Yeah, I mean, I see the analogy with the compressive strain for the tetragonal-like phase as well, right? So once you get to that new energy minima, you can lock into it. I just don't, are there substrates that you have in mind that would work in this ballpark? Like, what are they?
You mean those substrates?
Those are the ones right there. Oh, okay, I see.
Yeah,
I gotcha.
Yeah, I suggested the
Awesome.
substrates.
Yeah, sorry.
Those ones and yeah, for hexagonal phase.
Oh, okay.
Yeah, this one.
Great. Okay, great.
So have you thought at all about, you know, the chemistry of this system and whether or not there are stable, you know, vacancy ordering states here nearby when you try to make this? So for example, does this even, you know, this is a very large energy change from the perovskite, right? So do you start forming oxygen vacancies? Do you start forming mixed valence on the iron site? What happens? Have you thought about that at all?
Shortly, no.
Thank you.
Putting the stability concerns aside, we can just look at it as a model system for interesting frustrated magnetism. Are there other ferrites, iron-containing systems, that have similar frustrated magnetic order? And can you compare how the magnetism here would relate to the magnetism in some ferrites? Because I've seen similar frustrated magnetic order in other transition metal systems.
To me, I didn't notice other system have the similar frustrated magnetic structure.
To me, it's somewhat reminiscent of the manganites. And of course, those occur closer to equilibrium lattice constants. But you may find some interesting magnetic analogies where you could learn about the energy magnetism relationships and see if they still hold for this interesting metastable ferrite.
Okay, I think I can talk further with you. But I can let you know that since we are talking about bismuth ferrite, if we replace the ferrite to manganite, the phase diagram looks quite similar. It can also be stabilized in manganite, the two phases.
Any other questions? All right, let's thank our speaker and all the speakers of this session.
Thank you. Hi. Which one is yours?
Oh, I don't know.
I don't know.
Probably the one that's on.